Hello. Hello, welcome back to afternoon session of day one of ASCAT 2023. I hope you have enjoyed your break. Moving towards our next session. Now we have an invited talk by Katsunobu Imai from Hiroshima University, and this session will be presented by Professor Arindam Biswas, sir. Here's a brief biography about Professor Biswas. Dr. Arindam Biswas graduated from Jadavpur University, Kolkata, and received his master's and doctorate degree both from the Indian Statistical Institute, Kolkata. His research interests include digital geometry, image processing, approximate shape matching and analysis, medical image analysis, biometrics, and geometric deep learning. He has published over 100 research papers in international journals, edited volumes, and referred conference proceedings, and holds one US patent. He has served as a board member of the Technical Committee 18 for Discrete Geometry and Mathematical Morphology of International Association of Pattern Recognition from 2016 to 2021. He is currently a professor in the Department of Information Technology, Indian Institute of Engineering, Science and Technology, Shibpur, India. I'd like to welcome Professor Arindam Biswas onto the stage. Over to you, sir.
Hello. Good afternoon to everyone. You are welcome to this session. Let me introduce Dr. Katsunobu Imai. Dr. Imai is currently holding the position of Assistant Professor at Hiroshima University. He completed his Masters of Engineering and Doctor of Engineering from Osaka University. His field of research is informatics, principles of informatics and theory of informatics. He has over 20 academic papers on cellular automata published under his name. Over to Dr. Imai. Please proceed. Thank you.
Okay. Thank you very much. I will share my slides. So, okay. I am Katsunobu Imai from Hiroshima University. Thank you very much for inviting me to this very nice symposium. Today's my talk is about this. And so the title is about visualization of three-dimensional cell automata and tilings with head-mounted display. And yes, so let's start from some cell automata related topics. And the first is the game of life is, of course, you are familiar with, and introduced by Conway in 1970s. And another important cell automaton is self-reproducing cell automata introduced by von Neumann in 1950s. In a sense, this cell automaton is the world's first built-in cell automaton rule, a very complicated 29 states. And another impressive thing is introduced by Wade, also self-reproducing configuration, but the state is two-state on the game of life. So the rule is very simple, but configuration is extraordinarily complicated. And so playing with cell automaton, there are two scopes, discovering and building. And for example, interesting CA transition rules is, for example, life rule or 110, and I will show you later. A panic shooter rule is a discovered rule, but uh, for example, of course, von Neumann's self-reproducing cellular automaton and firing squad, the problem solution is built transition rules, and of course, in the case of configurations, discovered configuration is for example, a glider is usually emerged from a random configuration of the game of life. Uh, but building is, for example, of course, a von Neumann's cell automaton, and the glider gun is, of course, carefully built, and it is very interesting because the rule 110 is, of course, simple, but universality of 110 rule configuration is amazingly complicated. And I mentioned about the panic shooter is very impressive. So I'm not sure, but some of you do not know this rule, and this rule is the simplest discovered shooting game as far as I know. And the rule is a Star Wars rule and known from long ago, but some engineer find the rule is a shooting game. And I was actually amazed because let's just see the movies, and green spaceship and purple block is outside of the cellular automaton, but the other things is completely simulated by the only four-state rule, and amazingly enough, just shooting sometimes fire return back to very impressive, and it is actually a shooting game. And in my sense, I can't thought shooting game is carefully programmed. So it's a very complex program, but this rule is just for state. And actually a shooting game, so the emerged shooting game is very impressive for me. And so the two aspects, building and discovery, is very, very difficult thing, but anyway, life classmen try to erase the boundary. So this is very also you are familiar with, and light pattern is water via spaceship is this spaceship is carefully programmed to go to the direction of night move of the chest, and of course, very complicated lines computers movement. But recently, elementary night ship was found. The name is Salovin. Is the light pattern is it is also impressive and very surprising for me because this is a mixture of discovery and building. So I can't believe this is a very far from elementary night shift. But anyway, it is somehow emerged and modified to be the function of a spaceship. And of course, it is very important to develop simulation tools. And the game of life cases, there exists a killer application Goli. And thanks to the function of Goli, many impressive and complex cellular automaton was made. But despite the large number of 3D simulations of natural and social phenomena, of course, cellular automata-based simulation is usually a 3 dimension, but I think there are very little discovery or building of rather complicated cellular automata rules or configurations. Maybe there is no killer application to develop a 3D cellular automaton. So usually, if you want to build a three-dimensional cellular automaton, you have to made some simulator by your hand. And in such a way, we built a rather complicated three-dimensional cellular automaton almost more than 20 years ago. And this is a self-reproduction cellular automaton, and behavior is like this. So this worm-like structure goes through the cellular space. And just a few, very recently, just a few years ago, when I want to there are very old videotapes. We want to go through the such old videotapes, and I found simulator of when we developed the previous cellular automaton in more than 20 years ago, and this is this precise is not so large, and just power of CPU is very limited, and but anyway, we need some simulator to develop a three-dimensional cellular automaton. Of course, this is not so sophisticated, but anyway, we thought it is useful in more than 20 years ago. So at the time, it was very difficult to make any 3D CA due to the low computing power, but it should be different now. So computing power is amazingly improved. So it is actually easier to design a three-dimensional cellular automaton, but where to begin? And so anyway, how to go to the boundary of a discovery of building in the case, even in the case of a three-dimensional cellular automaton. And this is a three-dimensional version of a game of life. This is developed by Base, and several candidates of a three-dimensional life rule were proposed by him, but unfortunately, no definitive 3D life rules have been found. They are not so lively because the game of life is very lively. So this is just example of behavior of based candidate rules of 3D life. So the behavior is rather static and not to have a flavor of biological things, because gradually decreasing the number of live cells, but unfortunately not so lifelike. And there are some generalization of the game of life, but one extension is larger than life, is generalized life with expanded neighborhood size. And R is a radius of neighborhood. So normal life is radius 1, and larger than life is R is equal or larger than 2. And so the behavior turns to more level than the slow behavior, and it is there exists some very impressive rule. One is a Bosco's rule is like this, and in the case of a larger than life cell automaton, you can see some coherent structure patterns of named bugs. Bugs is a glider-like pattern, so it's translated to a specific direction. And the case of Bosco's rule, there exists a very impressive oscillator with period 166 Bosco named, is quite impressive oscillator. And combining these oscillator, you can build bug guns. So the analog of a glider gun in the game of life. And so once we try to build a three-dimensional bug, but we have no idea how to build. So first we try to make period 1 bug. So just translate it to a specific direction. And we found several period 1 bugs at the time. We tried to simulate collisions and for all offsets, and try to find some curious behavior, but nothing. At the time, no interesting collisions found. And so we gave up thinking about the three-dimensional CA after that, but augmented reality-based head-mount displays are focused again just more than 20 or 30 years ago. Such head-mount display is quite widely studied, but not so effective. But this time, we thought it must be impressive. So we try to discover the bugs again. This time, not to build, but not discover, because have we already have period one bug, and we thought there must be other period bugs around the period one bug. So try to modulate the period one bugs pattern, and we employ the heuristic approach to find some bugs. And one discovered bug seems to be impressive for us, and this bug has this rule has one impressive bug and several blinkers. So carefully placed such bugs and blinkers, we found turning and copying gadgets. So the combining these gadgets, anyway, we can embed logical circuit into the cellular space, the game of larger than life cellular space, and so this is a demonstration of a copying process of our bug and blinkers. So the light one is a bug, and the two blinkers are placed, and gradually goes to the direction of two blinkers, and causes reactions. And finally, blinkers were a bit modified, and dynamics finally goes to to change the shape to the bugs. And of course, without an explanation, I show you some snapshot movie of our tool. And anyway, this tool is programmed with this head-mount display. And this is another example of self-reproduction cellular automaton I have mentioned before. And 20 years ago, these simulation is too hard and takes many hours to make such movies. But of course, the simulation is real time and not so difficult. So the anyway, it is very hard to explain to you just with this movie. Using head-mount display, the scene is completely three-dimensional. So it is quite easy to understand, figure out the depth of structure. So I wonder how to explain. It is quite difficult. So if you have not yet have experience of VR or AR head-mounted display, just try it in the shop or showroom. And but anyway, employing a head-mount display, we can play with three-dimensional cellular automaton. But in the beginning, where to start from? But we thought we try to change the tilings because normally square lattice is normally used to simulate cellular automaton, but this device is you can easily understand the depth. So the other tilings and is possible to employ to simulate cellular automaton on such different tilings. So cellular automata usually have complex rules on square lattice, but so we thought employing just a simple rule, but allow to use very complicated lattices. So this is our motivation. So the simplest rule is a very simple diffusion rule. So neighborhood focused cell found state one cell in the neighborhood, then turns to the one. So very simply diffuses cells of one. And the rule is extraordinarily simple. So the square case, this is a Moore neighborhood and von Neumann neighborhood case. Both cases are starting from a single one state cell. Advancing the time, square gradually enlarged. So square and the triangular and the hexagonal tiling case is like this, and it is very impressive. Triangular case is enlarged shape is not a triangle but hexagon. Of course, these cases is quite easy to understand, but how about the Archimedean tilings? So Archimedean tilings are the 8 variations, and each case enlarged diffusion we called corona. The shape of a corona is this is a hexagon, and you can see a square hexagon. But this case is tiling is Archimedean tiling, but corona is edge corona. That is cellular automaton rule is von Neumann neighborhood. And this case here, very impressive. So in the first time we see this pattern of diffusion, I hardly understand why the shape is formed on the related tiling. So the above left is octagon, but not the length of edges is not the same, but quite impressive shape. And even the case of tiling, there exists not periodic called quasi-periodic tilings, and one of the most famous things is Penrose tiling. Penrose tiling is like this, and it is very difficult to when we start explanation explain the underlying mechanism of tiling is very impressive. But anyway, so we show that limit of the diffusion shape is a regular decagon in the case of Penrose tilings. So even in the case of a two-dimensional tiling, just employing a very simple diffusion rule, shape is far from trivial. So how about the three-dimension? So three-dimension tiling and corona is this is a square case, and in three dimension, adjacency as a neighborhood is von Neumann and Moore, and another face adjacent neighborhood is exist. So this figure is advancing evolving diffusion shape of von Neumann Moore, and edge adjacent. So vertex and edge adjacent and the face adjacent neighborhood. And even the case of a cube, employing different adjacency, the shape can be changed. So how about the other tilings? So even in the case of a regular convex polyhedra, there are many variations, and one is a regular polyhedra is very familiar with, and but semi-regular and regular polygonal prism is also exist, and gathering all the other convex polyhedra, there exist 92 types, and these polyhedra is called Johnson solid. So in the case of three dimension, of course, it is very famous because employing only one variation of tile, 5 parallel polyhedra can be tile all the three-dimensional space and these 5 cases. And but just employing 2 or more tilings, the shape is quite complicated. So for example, this is this shows 4 examples, and just watching these, but it is quite difficult to understand. So, for example, yes, this is a real-time generated shape tiles and employing horns, so you can make some actions. Of course, you have to make some program, but anyway, you can actually manipulate by hand. Of course, shape is completely virtual, but it is possible to observe the structure, and you making a reaction of your shape, your with your hand. So yes, so maybe it is quite difficult to so camera. Yes. Oh. Yes. Mm. これ、ダメか。Because ダメか。Sorry. We just made some control program of a camera, but it is not so easy to handle ongoing presentations because focus area is not so visible area is not so large. But anyway, it is, of course, it is very difficult to explain. But anyway, convex part or some depth is actually figured out. So using these head-mounted display, we can actually feel the tiling and the cell automata configurations. And so return to the topic of corona. So the this figure shows cube, and 466 is a traditional way of vertex face around the vertex, which tile is placed, is traditionally written in such sequence of number. But anyway, so shape diffusion formed shape is different, can be different when you choose the other adjacency. And this example is some very impressive shape. It is very hard to understand from the original figure, original tiling. So So the left bottom tilings or three shapes is quite different, and of course some of you feel the formed shape is something like a crystal or some related things, and so rocks or crystals. Of course, the cellular automaton is just a simple diffusion, but employing a tiling, this diffusion rule is can be regarded as a kind of a very simple model of crystal growth, and choosing a neighborhood may have some relation to the chemical affinity. And the finally, we try to build three-dimensional panel styling and observe with a head-mount display. Three-dimensional panel styling is three-dimensional analog of two-dimensional original panel styling, and this case is two polyhedra, acute and obtuse, and blue one is right hand is some planar area is built according to the inflation deflation method, and blue one is acute polyhedra, and yellow one is obtuse one, and so we anyway try to compute the position of a fairly large size of three-dimensional pendulum tiling, and using the head-mounted display, we made some program to generate a cross section of polygons, and the right-hand side is a cross section of 3D panel tiling, and so the acute and obtuse polyhedra combines a very complicated way, and I am not sure, but just cutting some making a cross section also generate a bit difficult computation applied to the original panel styling. But so far we have no idea. So this is closing of my talk. Anyway, we tried to play with three-dimensional cell automaton and the tilings, and how can we play with cell automaton on a three-dimensional display device? Because this head-mount display actually realizes a sense of depth. So, and we have already showed you. Of course, there are many limitations, but it is possible to manipulate with object by hands. So Maybe you can employ these display device, and anyway, a traditional way is employing a paper and a pencil, or even the case of a display, and uh, screen is completely limited to the just a two-dimensional plane. So even if you bring many large displays and just a two-dimension, but employing these type of devices, uh, you can overlay actual three-dimensional virtual three-dimensional configurations, the patterns to the real environment. And so I just ask you to advise me to how to use these VR or AR visualization to the development of a cellular automaton. Thank you very much.
Thank you, Dr. Umay. That has been a very interesting presentation. And now it is open to the floor for question answer session. Any question from your side, please?
What is the minimum size of the three-dimensional CA? That means, can we use as a size of the CA like n equal to 100, n equal to 30? Is there any boundation?
Yes. In my presentation, I employed configuration size is 50 times 50 times 50, but the limitation due to the computing power of this device, mainly due to the battery. But you can employ a larger desktop PC with GPU of enough power, and so the computing can be such desktop PC, and transfers three-dimensional image to this device is possible. In that case, you can extend a more larger configuration size with effective simulation speed.
And the second question is, can you use the Cellular Automata as a VR tool? That means virtual reality tool instead of AR tool?
Excuse me, they are cool. Because you mean heat problem of this device?
Particular, not that actually. I just wanted to know that can you use CA as the VR tool? That means virtual reality tool. Hello. Basically, three-dimensional Cellular Automata can you use as a VR tool, virtual reality tool?
Sorry, I try to gain the volume of. I'm sorry. Can you repeat again?
Yeah, sure.
No?
Is it okay? Can you hear me?
Yes,
Okay.
I gained the volume of my speaker.
My question is actually, can we use the three-dimensional cellular automata as a VR tool? That means virtual reality tool.
So the two-dimensional case.
Yes, yes.
I do not explain, show you. I did not show you, but we also try to simulate a two-dimensional cellular automaton in using this device with a time slice of each configuration can be stacked to make can be make a three dimension. And so the in the case of two sheet of paper, one-dimensional cellular automaton can be shown simultaneously time and space diagram, but employing this device, two-dimensional, for example, the game of life or some configuration can be simultaneously show full time-space diagram of two dimension, and it is very impressive to and easy to understand the time-space behavior. It is I think it is very useful usage of this device.
Okay, thank you. It's a good.
A question from the audience. Anyone else? And I would like to know that if someone online, if you want to ask a question, please raise your hands. We'll make them. Anybody?
Can I ask one question?
Okay.
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 Yeah. You tried to extend 3D tilings from cubes to any polyhedra. Okay. But
Yes.
when we study three-dimensional cellular automata, sometimes tiling is not important, but important thing is neighborhood connection in some cases. For example, I am interested in very simple three-dimensional cellular automaton with a small number of neighboring cells. In particular, we consider diamond structure that consists of carbon atoms. Each carbon atoms has 4 neighboring carbon atoms. But therefore, neighboring structure is very simple in diamond structure. But tiling is very complicated. Tetrahedron does not fill all the 3D space. Therefore, to consider such a 4-neighbor 3D cellular automaton, we need a very complex polyhedron. But when we study such cellular automaton, such polyhedron is not so important. Only 4 neighboring structure is important. How can you manage such a diamond cellular automaton in your system?
Yes, of course. Our first motivation is the cellular automaton, but we employ the simplest diffusion cellular automaton. So almost everything almost everything, if you find any difference, it should be comes from the difference of employed tilings. And of course, because each tile should have a certain geometrical shape, and space filling is very difficult. But it must be maybe some researchers of chemistry discussed about the order of short range or long range differences, usually coming from some quite difficult to explain, but some very small shifting gradually accumulate to the change of the shape. So in the when you discuss about the actual atomic structure or chemical molecular structure, related geometrical shape of polyhedra is not so important, because just shifting direction of atom, just making a very small shifting of certain periodic atoms changes structure of tilings dramatically. So even the case of quasi-periodic tiling, of course, actual tiling process is extraordinarily complicated. So it is almost impossible to tile such quasi-periodic tiling by in the process of nature. But just a small shifting causes global change of periodic tiling to the quasi-periodic tilings. So maybe even in the case of periodic tiling case, so the it is quite difficult to even if it is quite difficult to place completely space filling tilings, but if atom is periodically placed, you can find anyway, even if related tiling is complicated, it must be a periodic tiling. So as far as the diffusion rule, we call the corona shape, is anyway, in the case of periodic tilings, rough property is in a sense similar. But quasi-periodic tiling case is extraordinarily different. So there exists quasi-periodic tiling. The diffusion converges to a completely sphere. So it is very, it is quite far from my first impression.
Anyway, in your current system, we should give polyhedron to make to give neighborhood.
Mm.
We should.
No, because our simulation, tiling is completely calculated using Mathematica, and everything is not float approximation, but completely rigid computation. So the structure is anyway in the case of Penrose tilings, the cellular structure is computed by six-dimensional periodic lattice is employed to and three-dimensional projection generates the point vertex of a tile. So the anyway, we first generate the precise tilings. Even infinite case is also precisely computed.
Okay, thank you.
Thank you. Any other question from the online audience? Okay, if no, then I think we have come to the end of the session. Let us give big hands to Dr. Imai for taking his time off and devoting some time for this conference. Thank you so much.
Thank you very much.
Thanks to Professor Anindam Biswas for being the chairperson of such a nice session. I'd request Dr. Shukanto Das to present Professor Biswas a memento on behalf of the ASCAT 2023 team.
So, on behalf of organizing committee, it is my great pleasure to give this to Professor Biswas, who make this session great. Thank you, sir. And I would also like to thank Professor Imai for agreeing to give talk and finally delivered this beautiful talk. So you all enjoyed. Thank you, sir. Thank you, Professor Imai. Thank you.
With this, we have completed our first sub-session of this afternoon. It's time for a tea break. We'll assemble here exactly after 30 minutes at 4 p.m. Enjoy your break. Thank you. For online presentee, we'll be resuming the session at 4 p.m. Till now, it's break. Thank you.